I showed this earlier today. What I showed earlier was if you have, just to review, if you have a nonlinear model of your transistor, this particular example is for optimizing the output matching network of the main amplifier. So it's somewhat limited, but like I said before, when the peaking amplifier is off, this looks like an open circuit. So this is going to be a higher impedance, and when the peaking amplifier is on, this is going to look like a generator. So it looks like a negative resistance. So the impedance seen here is lower. So this will generate a higher output power. So this particular example has an optimization. Basically, it runs load pull simulations on a transistor and then uses the data to optimize the matching network for this main amplifier under those two conditions, the two different conditions, the two different loads that are seen. So, and then it's also a cross frequency. So it's hard to make Doherty's work across a band of frequencies, but that's the objective of this particular example. So it has load pulls at 3 different frequencies, and then it takes, well, it looks at the results. Takes the results and, okay, so I get these impedances, the Z mod and the Z opt impedances. Z mod corresponds to where you place marker M1, and in this case, M1 is on a 1 dB gain compression point near the optimum power. So I'm telling it, based on this data, if I look at the load pull simulation data, it looks like we can get a high efficiency near 40 dBm output power, and the high compression is going to be more like, or the high output power load is going to be more, or the output power is going to be more like 43 dBm for this particular case. So we want to optimize for this impedance at lower power, say 40 dBm power, and for this impedance at this power, which is at 3 dB gain compression in this case, and that's marker M2, which is on a VSWR circle centered on marker M1. So that's for one frequency, and then we did the same thing for the other 2 frequencies at 3350, 3450, and 3550 megahertz, and then we use this optimization to So we're attempting to take the data and optimize this matching network under the 2 conditions. One is a 50 ohm load, and the other is a 25 ohm load when the peaking amplifier is on. Okay, so the results are this. I showed this earlier this morning, but I also have a document, a PDF document, which goes through the details. So I don't know if this is enough for somebody to be successful, successful with it, but maybe. I think it's it's useful to read through this, and then you have a better chance of understanding what's going on and how the data is used in the optimization. But the result is this. Where's the optimization? Okay, yes. This is the result of using the loadable data in an optimization. And this shows that there is, I mean, ideally, these are the target impedances. And ideally, these optimized results would be right on top of the target impedances. They're not, but they're close. So, you know, I think this is a reasonable way to get close to an optimal design. And then this shows the performance that could be achieved. And these are the widths and lengths that were optimized in the matching network. Does this make sense, or is it too complicated, or is it? Maybe I'm not explaining it clearly enough, or I'm just curious. Does it seem too complex, or? I also have on the schematic. I have. This is the optimization schematic, and I have steps here that I'm trying to indicate what the steps are. You have to first run the load pool. You have to first run these load pool simulations at the different frequencies, and then you have to pick these optimal loads. This would be the Z mod, and this would be the Z opt load, and then you have to, you know, based on the data that you see here for power gain and efficiency, this gives you an idea of what could be achieved. These would be the ideal results. You probably can't get those from a matching network, but at least it gives you an idea of what the transistor could possibly produce. And this is a simple Doherty design. There are certainly more complex Dohertys. So you could start from this and create a more complex optimization, a more complex setup. So, okay.
Andy,
yes.
A customer asked about the Doherty characteristic because the Doherty has a very sensitive to the load flow dumping because it has a big peak here. So customer want to know which is better source to use the single the GW or the modulated signal source to define the performance. So which is better to use?
I've only seen a one-tone, at least for the load pool, I've only seen a one-tone simulation. But certainly, when you have the Doherty design, you'd want to test it with multiple tones and maybe a modulated signal. I mean, the example, the DPD example was of a Doherty PA with a modulated signal. So certainly you'd want to do that. But I've not seen somebody try to determine the optimal impedances from using a multi-tone signal, like a two-tone signal. I've not seen that, but I don't know everything, so it's possible somebody's doing that. Okay. I'm going going to show the this other workspace, which is a design flow. Let's find it. Okay. Okay. This is an example that I worked on a number of years ago. This is based on the people who created this example originally were with NXP, and the people at NXP are very knowledgeable about Doherty design. They work on, they create high power PAs and devices, and they know way more than I know about Doherty design. I only know a very tiny bit about Doherty design, but they're experts at it. And they had a workshop at the International Microwave Symposium in 2013. That was in Seattle. And this example is based on that workshop and the document as well. But they have a design flow where they go through the various steps for designing a Doherty. And they include DC analysis, small signal analysis, load pull simulations, designing the combiner, designing the input matching network, and then finally running simulations of the completed amplifier. And this goes through the details of that that analysis. I'm curious, has anybody seen this example before in ADS? Is anybody using this? Has anybody seen it? Nobody? Okay, this has been on our Knowledge Center for probably at least 5 years, maybe 6 or 7, something like that, maybe more. But it's if you're doing Doherty design, I would definitely get this example and take a look at it. It's probably worth reading through and seeing the setups. I think it's maybe you won't do it exactly the same way, but I think if you're doing Doherty design, you ought to look at these people are experts at Doherty design, and I think it's useful to look at what they did. Maybe you can pick up some ideas for your work. But this goes through the various steps of the process. It includes a DC bias sweep where we look at the expected efficiency for, say, Class B operation, S parameter simulations. This was a preliminary stability check. And then there are various load pull simulations that are included as well. So just looking at the workspace, the DC bias simulations, there are a number of different load pull simulations, and I've added this with the sweep up to the XTB gain compression and analysis point. Let's see. And then these here are the data displays that the NXP people developed. And these are specifically for Doherty analysis, and there are multiple pages, so you can look at data at gain compression, at constant output power. So these are efficiency, alpha power, gain, AM to PM distortion, they looked at the input impedance of the device, as well as a function of the load and the power level. They look at performance at back off. So this is 3 dB backed off from the X dB gain compression output power. And then there's you can look at the swept data and see how it varies across as you move the load to find an optimal load point, for example. So there's simulations of the Doherty combiner. You can run these as an ideal combiner, or this just enables you to see how the combiner behaves as you change basically. This is a test of what the output of the main amp sees as you change the loading due to the peaking amplifier being on or off. And R mod is either a large negative resistance, meaning it's basically off, or it's approximately minus 50 ohms, meaning it's on. So it's looking like a generator, or it looks like a negative resistance in this case because it's generating a signal, which is a little different way to think about it, but that's what it's doing. And then you can when you're running these simulations, you can make these elements more physical rather than just ideal transmission lines. So depending on the how you're going to physically implement the design, you can use models that are more realistic. These are still very ideal transmission lines. So you can certainly you'd want to use EM simulation here, ultimately. Okay. I found it useful to. The behavior of a Doherty is to me anyway. It's not intuitive. It's complicated. So I found that running some simple simulations on different parts of it helped me to understand how it was behaving. It just helped my understanding of it. So I think that ADIS is a useful tool for that sort of analysis, because you can make things ideal and then add complexity. I mean, if you make it ideal, it's easier to understand, and then you can add complexity to get closer to the reality of a more realistic design and see how things change. Okay. This is, maybe I already showed this, but the output matching network. Yeah, there are a number of different load pools included here. You certainly don't have to do all of them. You can pick whichever one you want to use, but you certainly don't. Yeah, like you don't have to do all of them. Certainly. So this is an optimization of the matching network. I already showed this here. So we found the optimal loads, the Z-off. What they did was they just typed into a text file Z-ops. These are in the data directory. Oh, okay, here they are. So they typed. type the optimal loads into an MDIF file, or I'm sorry, into an S1P file. These were found from looking at the simulated load pool data at different frequencies, the real and imaginary parts of the optimal load impedance, and then they just used these values in the optimization here. And the way they do this is they set okay, Z mod simulate. Okay, yeah, so Z opt is read in from the Z opt file, and Z mod is read in from the Z mod data access component. So it's read in from this file, and those values are used to set the term impedance. So when the optimization, if the optimization works successfully, then the load seen looking to the right is because this is the conjugate of Z mod. So that ideally, if you can drive the reflection coefficient to 0, then this would be Z mod, and so you're able to generate the Z mod impedance, and that's the case with. That would be with the transistor, the peaking transistor off. That's Z mod, and then with the peaking transistor on, this is Z opt. Ideally, looking to the right, and this and this are the same. These two happen to be are the same network. So that it's the same set of values we're trying to optimize under both loading conditions. Does it make sense? Yeah. Okay. Okay. And then this was the once you've optimized that, then you can optimize the input matching network, and then finally we have and a simulation, several simulations of the completed power amplifier. And this is one of them. Let's see. This shows the Doherty PA response, the overall response for gain versus power delivered for, and efficiency versus power delivered for 3 frequencies, across the frequency band. And we also have a frequency sweep. So this is in this case, we're sweeping frequency and also sweeping the bias. So I'm sweeping the gate bias, which sets the power required to turn on the peaking amplifier. So as you change that bias, the power required to turn on the peaking amplifier changes, and the gain compression and the power out efficiency curve shapes change. Then we're also sweeping frequency as well. So the result is this. So for these are the curves for gain and efficiency. This is close to what we want. We want to have a high efficiency over a range of output powers. That's the whole objective of the Doherty. You want to get high efficiency. You don't want just high efficiency only at one output power. You want a range of output powers still get high efficiency. So that looks pretty good. That was with the gate bias for the peaking amplifier at its lowest value, and as I change it to a higher value here, the performance degrades. That's not as good. So, but you can vary other parameters and maybe get a better understanding of how the design is operating, or what trade-offs could be made.
I have a question.
Yes.
Is that the optimization depends? Since there are many parameters input power vary, and then the matching circuits change. So how do you define the goal in the optimization? Maybe not just the one input power. Then how do you define the optimization goal? Can you show us
Do you mean on this schematic?
the final, the complete?
This is the complete amplifier.
Yeah. Is there since the optimization test bench? So what is the optimization goal?
Yeah. In this case, the only thing that's actually being optimized, I'm only using the optimizer to find the XDB gain compression point. It's the.
So you mean just final as a 3 dB compression?
Yeah. That's all I'm using it for. I'm not actually optimizing.
If we achieve that goal, then maybe the before maybe lower than the power level, maybe also improve the efficiency. That is that way.
No, I'm sweeping. It's a
So
little bit.
you sweep the input power, right?
Right. Yeah. What I did was I want to find the input. Well, the way this works is I have a multi-dimensional sweep. I'm sweeping the peaking amplifier bias, and I'm sweeping the source frequency. And then for each combination,
Can you zoom in the optimization goal? Goal.
There's a bunch of them, and it's.
Goal is not just a number.
No, it's a multi-dimensional optimization. It's this situation again from the load pull presentation. The optimization is doing this. It's this sequence of steps. That's all it's doing. Is I want to find this point for each combination of input of peaker bias voltage and source frequency. I want to find this point. Currently, you have to do an optimization to get that point. So that's all the optimizer is doing. It's not doing anything else.
But it looks optimization goal is multi-dimensional, not just.
Correct. Yeah.
Oh, okay.
Yeah. It's multi-dimensional. Yeah.
Thank you.
It's multiple steps. Yeah. And R&D is adding a capability to find the XDB point relative to the peak gain. So this complex optimization sequence will no longer be necessary. I think that's coming in a near release. That will be a big improvement.
네, 지금까지 그 더티 설계 관련해서 저희가 지금 초반에 ND 하원씨께서 얘기를 하셨던 것처럼 저희가 그 간단한 워크샵, 그 트레이닝 워크샵 자료들이 널리시 센서에 올라가 있습니다. 그래서 더티 앰플뿐만 아니라 이제 다른 형태의 형태도 있고요. 로드풀 관련해서도 트레이닝 자료들이 이제 널리시 센터에 있으니까 한번 가서 보시면 될 것 같고, 그 마지막에 설명을 드렸던 것처럼 그 도어티 앰프의 퍼포먼스를 최적화하기 위해서 저희가 이제 여러 스텝을 통해서 또 옵티마이제이션을 돌려서 결과를 찾는 그 스텝들에 대해서 설명을 좀 드렸고요. 이 서로 트레이드오프 되는 부분에 대해서 이제 멀티플 골을 집어넣어서 이제 한 번에 찾으실 수 있도록 하는 부분도 이제 제공을 하고 있다까지 설명을 드릴 수 있을 것 같습니다.